Okay, good morning everyone, and welcome to this short courses on biomineralization. We are very happy to have you all here, and I hope you will enjoy this week all together, open for learning new things and having a lot of discussion all together between different communities. So to start with, a small introduction about how these short courses were started, where they come from, and why we are all together here. Initially, as Florence presented just before, it was starting from our biomineralization axis in this Labex Matisse. And in fact, it started when Karim Benzerara came and told me it would be good to try to make these communities working on biomineralization, working together and discussing. What is very important in this biomineralization is interdisciplinarity, because it's really a topic which gathers a lot of different communities. So we decided to, through this Labex Matisse, trying to set up this school. Then we needed money, of course, so we went to the CNRS with this project, which was really trying to unify the different concepts and techniques which are involved in this biomineralization. Hopefully the CNRS was happy with our project. This is where we started to do these short courses. So here is the organizing committee that was involved in the preparation of these courses. So if you have any kind of problem, just come and see them. They will be happy to help for any kind of issues or questions about the meeting. We then had the chance to gather a scientific committee, which comes from everywhere in France, with a very broad range of expertise, from paleontology to medical science. And we are especially happy to have Philippe Janvier, which was involved in the scientific committee, which was just elected in the French National Academy of Science. So it's really an honor for us to have him here in this committee, of course, and here today, and to present his work later on during this week. So here is a program. So we have 11 talks with invited speakers. We will have also 18 short talks, which will be gathered all around this week, and also 2 posters, which will be presented in 2 poster sessions on Monday and Tuesday. Just a few words about the places that you will meet and where you will be during this week. The first one is here. Les Cordeliers. So Les Cordeliers is an ancient abbey, which was under the rule of the Cordeliers monk. Cordelier means rope, so because they have a small rope there around. And it was funded by Saint Louis, so it goes very, very far back in the Middle Age. Very interestingly, this was also a very specific place during the French Revolution, where there was some important meetings from the people for human rights, especially, and citizenship. Then in the 19th century, it became an hospital and a school of medicine. And then in the 20th century, it became a practical school of medicine for the university, which is just beside. Then for some time, it was not used, and you see in the 1970s, the university bought the buildings, and it's now a research center, and also there is some administration desk in the campus. Tonight, you will also go to the Tour Zamensky, which is the main tower in the Jussieu campus, which was completely rebuilt when there were works due to asbestos on the campus, and you will go there for the cocktail on Monday evening. With a wonderful view, you have to see that, especially at night. And of course, most important for this week is you as participants. So a few numbers. You are more than 90 participants, 50% postdocs and students, and 50% permanent researcher. I think it's a very good numbers. 15 to 20% people comes from abroad, so thank you for being here. And a good number also, 50% women, so I think it's quite a good number for our scientific community. And as I said, this is really interdisciplinary, because we have people coming from more the human science and to poultry research. So really a broad spectrum of expertise and people interested in this field of biomineralization. So just one word to say that Karim has been contacted by this journal, which is called Minerals. This is an open access journal, and they offer to edit a special issue on biomineralization. So of course this is an open access, so some of the publication will have to be paid, but there are some possibilities for invited contribution. So if you're interested, just contact Jennifer, Karim and I to see what we can put together for this special issue. But there is nothing required, it's just if you want to take this opportunity. So as I told you, the key words probably in these sessions will be interdisciplinarity. So there are many ways to look at interdisciplinarity. This first cartoon is really probably what should not be done, which is a list of introducing biology to physicists or to geochemists and whatever. It can be a very long list. Of course, this will be part of the aim of these sessions for everyone, but it will not be that strict, and we really want to have exchange so that you can exchange between your own background and what the other people are doing and try to teach. The other way of looking at interdisciplinarity is another bad side of things, is mixing people that have nothing to do with them, although it can bring to very interesting and funny experiments. As a matter of fact, this interdisciplinarity was put aside and emphasized, I would say, by two of the main initiators of this biomineralization topic, which are Lawenstam and Weiner, which were the first to really define biomineralization as a processes where living organisms form minerals. And also they really show that biomineralization is at the center of what they call this biomineralization wheel, where you really saw that biomineralization is connected to many fields which come from chemistry, which goes from biology, earth science, and physics. So it's really enlightened the diversity of expertise which are needed to study, understand biomineralization, and this is really what we tried to do and to propose you during this course. If you think about what biomineralization means, you can consider it as a scientific oxymoron, because what you have on one side is bios, the Greek word, which is life, and life is usually considered as something which is animate, which has some plasticity, which is soft. And on the other hand, you have mineralis. Mineralis comes from the Latin and mean coming from a mine. So once again, a mineral is something inanimate, it's something stable, it's something hard. And I would say that biomineralization is a meeting between, I would say, DNA and this silica tetrahedron arrangement in minerals. So first question we have to face is, who is doing biomineralization? So we have this wonderful tree of life, thanks to Purification Lopez Garcia, which show you the biodiversity of organisms which are involved in biomineralization. And you see, you can find them in bacteria, in archaea, in eukarya, and in many different kind of species. So biomineralization is everywhere in the tree. This is very important. And once again, animals and plants, which we can have access more easily, are only a small fraction of these organisms which can do biomineralization. And once again, it's very important to consider that there's probably much more organisms which are able to do biomineralization. And so it's very important to look for new systems and for new models, because the more we have models, the more we will be able to understand and trying to see if there is some trends in the strategies that are used by living organisms to make biomineralization. So this diversity in terms of biology, it also has a mirror in the diversity, chemical diversity, I would say. So for a chemist, you have to look at the table of elements, periodic table of elements. And what I put in red are the elements which are known to be biomineralized by living organisms. What I would like to point out is that there is a few of these elements, especially metals, which in fact have been discovered in biomineralization very recently, and not in, I would say, natural conditions, but through what is called artificial biomineralization, which means that you have an organism and you put him in the presence of these inorganic ions, for instance, and you look what's happening. And sometimes, very often, they will just die because they cannot cope with the elements that are in contact, but sometimes they are allowed to take these elements and to put them into a biomineral phase. So once again, artificial biomineralization is something which is very important if we want to go on exploring biomineralization. The second point, which is very important, is why biomineralization? So this is, of course, a very complex issue. I would say here the key word is evolution. what happened is that living organisms have grown and developed in the presence of inorganic species. So in a way or the other, they have to cope with it. But of course, we know that evolution makes things trying to use what is their environment. And if this use is a good point for their evolution and survival, then they will keep it and develop it. So as you know, of course, inorganic ions, they are widely used in the cells as ions, for example, for the regulation of cell metabolism, like calcium, like all alkaline earth ions. They are also involved in controlling protein conformation, and of course, they are used for signaling, especially in neurons, and for electrical transduction. Now, if you go from the ions and you think about biomineralization, you have to go from ions to condensed phase, which means that you gather together a number, large number of ions together to make something which is condensed. So there is probably two reasons for getting this condensed phase, which is probably for the storage of these ions. All organisms, they have storage, so that if there is something lacking around in the environment, then they are able to take it out and use it. The other aspect, which is strongly related, is detoxification. If there are ions, if they are harmful for the organism, then one way to make it less harmful is to turn it into a condensed phase, because these phases are less reactive than the ions, which make them more easily to cope with by the organism. And finally, it's very important to know that this condensed phase, which has initially a role for a very basic role, then the organism during evolution realized that they can be used for properties, intrinsic properties as materials. So this is where you go from condensed phase to a useful condensed phase, which is a material. In this regard, we can just look at this biomineralization as a way to survive. So here are two examples of basic survival strategies. The first one is illustrated in gastropods, and these gastropods, some of these, they have some calcium phosphate, amorphous calcium phosphate particles inside. And when they are in the presence of metal ions, which can be toxic, what's happening, in fact, is that this calcium phosphate, it can dissolve. So the phosphate is kept inside the cell, the calcium is withdrawn, and the phosphate can go and interact with the metal. And as you know, metal phosphate are very stable systems, poorly soluble, so they will precipitate easily. And because they are precipitate, the cells know to deal with them, and once again, to excrete them. So really, this calcium phosphate probably was initially storage of calcium and phosphate, but it also becomes a way to deal with toxic ions. The other example that you're probably well aware of is this discovery of bacteria which are found in a gold mine. And once again, gold can be toxic for a lot of cells, but to deal with this problem, these bacteria know how to reduce gold. And reduce gold ion means turning ions into particles, okay? And dealing with this particle, which is like a reduction process that we can do by chemistry, but by doing that, they are doing these particles to avoid the toxicity of the metal. The other way to consider biominerals, once again, is as materials. So the real question is, what can we do with inorganic materials that we cannot do with organic materials? Because if everything can be done with organics, then why using minerals? So of course, if you think about organics versus inorganics, one of the main properties of minerals are their mechanical properties. So mechanical properties is a very broad term which have different way of being mechanically active. It can be used as a scaffold. This is our skeleton. It can be used as a protection, as a shell against the predators. It can be used for attack, and this is the example of a shark tooth, a very big one, and we will talk about it later on in these sessions with the talk of Matisse apple. It can be a defense, like in this urchin spines, and also for anchoring. You already know these small organisms that need to stick on the rocks nearby the sea, and to avoid to be taken by the sea when there are some waves. So to stick on the rock, they need to have this anchoring system which are stronger than the rock, to be able to stick on the rock. And to do that, they are preparing this kind of claws which are made on iron oxide and iron sulfide system. So once again, mechanical properties of these inorganic materials. Another specific property of inorganic material that you can tailor depending on the phase you're forming is their density. So density is what you found in otoliths. So you know otoliths, they are small particles that are in the inner ear and which allows you to find your equilibrium. And these are, of course, mineral particles, and their density is very important to be able to sense gravity. Magnetic properties, of course, magnetic properties exist in the organic matter, but it's a very poor one, poorly stable, very dependent on temperature. And if you're looking for a magnet, then you look into inorganic material. And this is what these magnetotactic bacteria are doing. They are doing some nanoscale magnets that are useful for orientation in the environment, and you will have a talk later on about this aspect. Other aspect of inorganic matter, chemical stability. Once again, you know that organic matter can be easily hydrolyzed or destroyed if you go into very acidic conditions or alkaline conditions. In contrary, there are a lot of minerals which can be stable in rather harsh conditions, acidic or basic conditions, and this is the case for this kind of microbes which live in a very acidic environment. In this condition, the proteins or polysaccharides would have been hydrolyzed. So to avoid this problem, they became coated with silica, and you know that silica is quite stable in acidic conditions. The other interesting of that is that they selected silica because it's transparent. And these organisms, they are photosynthetic, so they have a protection, a chemical protection, but still they can get access to the light, which is necessary for survival. Last example about the optical properties. Once again, you know, in optical devices, when you want to be able to control the light transmission, it's very good to have very nice crystal with a very good orientation. And this is what these organisms have been doing. They have been growing crystal with a very perfect orientation so that they can get light and focus it on their eye. So once again, using the specificity of the inorganic materials for a given property. So to give you more insights about these two aspects, we will have first a talk by Professor Peterson from Dartmouth University that will explain you more what is the evolution of biomineralization, starting from the Precambrian to now, and to show you what is the correlation between the change in evolution and the biomineralization process. Then, as I mentioned already, Matisse will make a presentation about what are these peculiar properties of biominerals. It will show you many different kinds of structures, many different kinds of properties to show you why biominerals are interesting and why they are fascinating. Then, when we try to understand why we have biomineralization, the big question is, of course, how biominerals are made. How, of course, is, you know, a very complex question. And once again, what is appealing is the ability of organisms to control the structure and the shape of this inorganic material. This is a very well-known example of diatoms. So these diatoms are making silica shell, but you know that what is fascinating is this ability to control the structure and the shape from several micrometers to a few nanometers. So the question is, how can they do that? And this becomes even more striking when you go into crystalline phase. For example, this is calcite, as you can find in geological conditions. And this is exactly calcite, but this is what was done by coccolithophorids. So once again, the same chemical composition, but very different shape. And you go from something which is very rigid, you look like this, at something very soft, with a lot of curvatures. And not only that, but what the organism can do is to select the crystallographic phase of your material. So going from calcite to aragonite, then once again, this is a geological phase, and this is what it looks in corals. So this ability to control crystallography and shape is something which is really challenging and that we cannot really do just by chemistry. So how it's working? Well, that is probably all you know, and there are two experiments which are key to start to understand what's happening there. The first one is the one you can do when you take a crab shell, and then you can cut in two, and one piece you will add bleach, so you will end up with getting rid of everything that would be organic, and what you end up is this calcium carbonate crystals. So you can say crab shell is mineral. But now, if you take the second half and you add this acidic molecule, which is able to catch calcium, which means that if there is some calcium phases, then they will be dissolved, then you end up with this. And this is an organic part. This is chitin. So it just shows you that biominerals are not purely minerals. They are always composite materials. And this is very important. A second experiment, which has been really a key in this field, is this experiment made by Belcher now nearly 20 years ago. What they did in this work was to first extract organic matter from nacre, and they just spread two parts, one which was an insoluble part and one which was soluble. So if you take the insoluble part and you mix with calcium and carbonate, what you happen to get is this kind of cube you see behind, which is calcite. Okay, what you're expecting is you do it in your lab, you just mix calcium and carbonate, and you get calcite. But as soon as they added these soluble extracts of this nacre, then they end up with seeing the deposition of aragonite. So once again, it means that the system is very reactive in that the organic matter in the shell is able to control the morphology and the crystallographic phase of these biominerals. So to go further into this aspect, we will have several presentations. The first one will be given by Dennis Gerbauer from the University of Constance. And the idea of this talk is to introduce the very basic physical chemistry of nucleation and growth, and to understand how a mineral is formed, and ultimately to understand how organism can control or modify this mechanism of nucleation and growth. Then we will go on the other side, more on the biological side, and we will have this talk by Frédéric Marin that will show you how you can relate the diversity of proteins with the ability of these proteins to control the mineralization processes. And finally, we will have a talk on magnetotactic bacteria, which will be given by Nicolas Mengy and Christopher Lefebvre. The interest of this is that it will really parallel the biological and the mineral world to show you how it's possible to understand how these magnetotactic bacteria are working, but also what is really the mineral characteristic features and properties of these iron oxide particles. Then, of course, there is an area which is very important in biomineralization. This is what I would call human biomineralization. As you can see here, this is a table of the elemental analysis of the human body. So, of course, you start with oxygen, carbon, hydrogen, nitrogen, which is the organic matter, okay, our organic part. But then there are two elements, which are calcium and phosphorus. So it's not a surprise, but if you look at the way, for instance, calcium is distributed in the body, you see that most of it is in the bone, okay? So coming back to what I said later, the bone is usually considered initially as a reservoir for calcium. If you can have exactly the same figures for phosphate. Once again, there is a lot of phosphate. A lot of it is intracellular, but most of it is stored in the bone, okay? So at the end, your bone itself represents 10 to 15% weight of your body. So biomineralization is a major part of our body, and it's, of course, of paramount importance. So not only it's important, but when you try to understand what's happening, you realize there is an increase of complexity in this system. As you know, bone itself, it has at least two different kinds of bone. And if you go to tooth, once again, you know there are 3 layers of bone-like tissues in tooth. And these different tissues, they have different level of organization and different level of mineralization. So the tissues themselves, they are really complex. But if you look at the two sides, the mineral and the organic part or biological part, the mineral itself is complex. A lot of people would say bone mineral is hydroxyapatite. You know, it's not true. It's in fact a non-stoichiometric hydroxyapatite, which is partially carbonated. So it's a very complex mineral itself because it has to be very reactive. And the same is true for the biological side. You know, there are many proteins and molecules which are involved in bone formation. So, of course, this system intrinsically from the mineral and biological side is a very complex one. So, other aspects which are relevant to human biomineralization is, of course, every kind of bone defects that can occur. This is just a breaking of the bone. This is what can happen to your teeth. And this is a case of osteoporosis. And of course, if we want to heal bone, then we have to understand how it's working, how it's made in order to be able to repair it the best possible way. And of course, when it goes to another kind of pathology, which are pathological mineralization, which means formation of minerals which are either not the good phase or which are precipitated in parts of the body which are not supposed to be mineralized, then we have a much larger diversity of mineral phase which are formed, which can be calcium part or phosphate part, but a wide diversity of mineral phase are formed by the body if something is going wrong. So once again, to address this point of human biomineralization, we will have two talks, one which will be given by Christelle Combe, that will give you the physico-chemical point of view on bone formation and tooth formation, and its outcome for bone repair. And we will have the point of view of the biologist and the medical doctor to show you how this mineralization is regulated by some of these proteins. So really covering again this range between chemistry and biology. Another very important aspect of biomineralization, and it concerns a lot of you here, I know, is the relationship between biomineralization and time. Of course, biomineralization is a record of the activity of a given organism in a given environment. So whenever you change, you can have the problem of the evolution of the organism itself, and of course the evolution of the environment conditions, which can be temperature, which can be CO2 pressure, and whatever. And both of them will leave a trace in the biomineral. So to study that, you really need to gather a lot of different techniques which will allow you to look at the system in a very large way. So it can go from isotopic measurements, especially for time parameters. You can go to biology, which can be like PCR to get access to the gene and the molecule produced. A lot of microscopy to see the structure and trying to see the interface between the biological part and the mineral part. And you can go to much shorter details. This is, for instance, FTIR that will give you an idea of the chemical composition of your material. And ultimately, you can go at the atom level using, for instance, NMR that will give you the environment of a given ion in the whole material. So I have absolutely no action in this book, but I think it was important to point out this recent publication which gives you an insight of all the techniques that can be used to characterize biominerals. And I would like to point out that in this book is also mentioned molecular simulations. So this will not be really addressed in this course, so I just like to give you an example of that. This is a recent study which was interested in otoliths. So you all know what otoliths are, and these are two images of two different otoliths which are made in fishes from two different seas. And what you see here is that you have alternance of white and darker part of the otolith, which correspond to different levels of mineralization. And what was interesting, in fact, is to understand why these two organisms have different layers, one where you see much more darker and one where you see much lighter layers. So this is exactly what I mentioned. In the case of otolith, there is two sets of parameters which can explain how this shell is formed. The first one is really related to the living organism itself, the fish, and how its metabolism can change. And the other one is more external reason, which is environmental reason, which is the food available and the change in temperature. So by monitoring to distinguish between the temperature effect and the fish metabolism effect, they were able to make very nice curves about the variation in mineralization with time, depending on the region where these fish were growing. And finally, the simulation, you see, very nicely fit the real otolith that was formed. So it's really an insight about the interest of simulation. Lastly, another really important aspect of relationship between biomineralization and time is the ability of biominerals for preservation. One aspect of this is given this in a very interesting work where the people look at the amino acids that were present in water and in the sediments. So this is this pool of amino acid. And what is written here is that if you compare, as a function of depth, the amount of amino acid that you see going from up to down, you lose about 30% of the amino acids. Now, if you look at the amino acids which are associated with calcium, then you see that you have no loss of organic matter from the bottom to the top, from the top to the bottom, sorry. And the reason is that these amino acids, they are associated with biominerals, so that they are preserved inside the mineral, and you can find them back in the sediments. Another very interesting thing, of course, is that this preservation depends a lot on the kind of amino acid which are associated with the calcium, and the ones which are preserved more are the ones which are known to be associated with the mineral inside the shells, for instance. Another important aspect of biomineralization and time is related to preservation of cultural heritage, and this is an example, but you probably know many of them, for the preservation of old stones, where what people have been using are bacteria which are able to biomineralize, which means that they are able to produce new stone that will ultimately reinforce the stone that was degraded over time. So, to address this topic, we will have two presentations. One from Anders Meiboom that will tell you more about the relationship between biomineralization and paleontology, and especially how you can use or not use biomineralization as an indicator of change on Earth and sea. And on a very different aspect, but very interesting and original, we will see the relationship between biomineralization and archaeology, and how these different biominerals, which are found in many forms of art, can be used as a datation and to know how the people have worked on these natural materials to make these different objects. So ultimately, and this coming back to what I said at the beginning of this presentation, really biomineralization is bridging two worlds, the lithosphere and the biosphere. So this interface is very rich, as I've shown you. There are very different ways to bridge them. For instance, prebiotic chemistry or extreme conditions are a way that the minerals can interact or influence biology. And on the other hand, the field of geomicrobiology, which is quite emerging still, is a way to understand how biology and how life can control mineralization. So I think it's already a good overview of this field. So to address this interesting point, we will have a presentation by Juan Manuel Garcia Ruiz that will present some interesting insight about can we use biominerals or apparent biominerals as traces of life. And he will try to show you that all these forms, which looks like biominerals, in fact are purely inorganic materials. So this will raise a lot of interesting questions. And ultimately, to go to a larger scale, we will have a presentation by François Guyot that will try to relate biomineralization, which is something which happens at the scale of an organism, to global geochemical cycle, which means at the Earth scale. So through different examples, he will try to relate the micro and even the nanoscale to the Earth scale, and I think it will be a very good way to conclude about this biomineralization field. So finally, what we are proposing you in this week is a journey, a very diverse journey through concept, because we will go from nucleation theory to phylogenetic trees, so it's really a broad range of concepts and disciplines. In techniques also, we will go from gene analysis by PCR to the use of synchrotron radiation to elaborate and understand how biominerals are done. It will also, as I mentioned, be a travel through space and scale. We will look at the tetrahedron of phosphate ions and ultimately go until the Earth scale. And of course, in time, because we start from the very beginning of biomineralization process in the Precambrian to our current Anthropocene area with all the problematics of bone and tissue repair. So finally, I think it's important to leave the final word to someone who has the very perfect name for this short course, which is the Dr. Livingstone, so you cannot make it better. And I would like to join him to say that we are very thankful for being here and for welcoming you to this short course. Thank you very much.